We are going to start a new lesson today on solutions, and solutions covers a lot of different topics that we've already talked about, so you'll have some review material. For example, we'll talk about properties of solutions as well as provide examples of solutions such as the air. We'll be calculating concentration several ways: molarity, molality, mole fraction. Molarity is something you've seen before. Some of the reagents you've used already, such as 1 molar, 6 molar, and you'll eventually use 12 molar hydrochloric acid. That indicates the concentration. We'll talk about how to dilute a solution, and you'll be doing that in the lab. We'll be reading and analyzing a lot of solution-based graphs, and you will be generating solubility curves in the lab using potassium nitrate as a solute. And then finally, we'll be calculating freezing and boiling point of solutions. We'll talk about why they salt roadways up north when it snows. We'll talk about why you put salt in water before you boil it to make pasta and other foods. And then finally, we can determine the molar mass of a solution from freezing point or boiling point data. So a lot of different topics we're going to discuss in this chapter. We'll start off very basic. And in regard to solutions, a solution is any substance. It can be a solid, liquid, or gas that's evenly dispersed or distributed throughout another substance. So for example, one of the things you have on the table for Passover is salt water, and you wouldn't know there was salt in there unless you actually tasted it. Sugar water would be another example. That's one substance dissolved completely in another substance, so it's made up of at least two different materials, but it looks like one. And a solution is a homogeneous mixture. It contains more than one material. A heterogeneous mixture also contains more than one material, but you see at least two materials if it's heterogeneous. For example, oil and water, oil and vinegar. You can see at least two materials. Granite would be another example. In Florida, we go to the beach a lot. You can see shells and all types of rocks in the sand on the beach. That would be heterogeneous. This chapter is going to talk about homogeneous mixtures, solutions. When you make up a solution, remember the solute gets dissolved and the solvent does the dissolving. If, for example, you have a liquid solution such as 70% isopropanol, what you would find with 70% isopropanol is that 70% alcohol, 30% water. And we talked about this at the very beginning of the year. So if, for example, you had, let's say, 30% isopropanol, which is rubbing alcohol, although rubbing alcohol typically is at 70%. This is 30% alcohol and 70% water. So if you were making 100 mils of it, you'd put 30 mils of this in and 70 mils of this. And in this case, this would be your solute because it's of the lower concentration, and this would be your solvent because it's of the higher concentration. In contrast here, you'd have 70% alcohol and 30% water, and in this case, the alcohol is the solute and the water is the solvent. So whatever you have more of is the solvent. That's what does the dissolving. The solute gets dissolved. And there are many examples of solutions. Rubbing alcohol, typically at 70% isopropanol, that is a solution made up of a solute dissolved in a solvent. Other examples in your notes include salt water, sugar water. You would know it was a solution because you could go back to the component parts. If you had salt water, you could boil off the water and you would be left with the salt residue. Same thing with sugar water, although you'll probably get it to caramelize and have a big brown mess. Air is a mixture of gases. You've got oxygen gas, carbon dioxide, argon, all dissolved in nitrogen. The chief component in air is nitrogen gas. Brass faucets, we talked very briefly about alloys at the beginning of the year. A brass faucet is a solid solution. So again, when we think about solutions, we tend to think about liquid solutions, but solutions can be gases such as the air, solids such as brass, and primarily liquids, which we use in the lab all the time. So a brass faucet is actually an alloy. It's copper and zinc mixed together. It's actually a substitutional alloy. We'll get into that more in AP next year for those of you moving on. Antifreeze is a liquid solution. You've got rust inhibitors as well as rubber hose conditioners, all dissolved in ethane diol. So that would be your solvent. This is an organic solvent containing carbon. Most solutions, as I said, are solids dissolved in liquids, but there are actually 9 possible combinations. So what you're focusing on here is in this first grouping, you've got the solvent as gas. In this grouping here, you have the solvent as liquid. And in this grouping here, you have the solvent as a solid. And I mention that because whatever state of matter the solvent is in will be the state of matter for your solution. So if your solvent's a gas, your solution is a gas. If your solvent's a liquid, your solution is a liquid. So for example, you can dissolve either gas, liquid, or solid in a gas, and you will get a gas solution. For example, I'm sure how many of you go diving? Nobody goes diving?
You go what?
Diving? Like scuba diving or something? With a tank, you've gone diving, and you have a tank, and it's not just oxygen, right? No. It's actually helium that's dissolved in oxygen. They have found this to be better for numerous reasons, and I'll let you look that up and explain to me why that is better. So you have a gas dissolved in a gas. In Florida, it is very, very humid. You have the humidity, that water dissolved in air, and that makes for beautiful curly hair. Up north, they called it, what they call it, frizzy hair day? It's not a good hair day? I can't remember what they said. Down here, there's no good hair day. Naphthalene dissolved in air. This is a solid that will naturally just dissolve in air. Another example I can think of up north, we used to wear sweaters because it was so cold, and we would put mothballs in the closet because the mothball was the solid that would dissolve in the air, and the smell of it bothered the moths, so much so that the moths would keel over, and then they wouldn't chew your sweaters, so your sweaters wouldn't have holes in them. Some of the air fresheners, those plug-ins, are solids, and they will dissolve in the air and produce a scent that can make you very sick. Never leave those in too long because they can get moldy, and if a kid goes and sniffs it, they can get really, really ill. There was a child, a friend of a friend, who actually developed brain damage from one of those plug-ins. So don't leave them sticking around too long because they can be very dangerous, especially to little children. If your solvent is a liquid, again, you can dissolve a gas, liquid, or solid in it. Soda, carbon dioxide is a gas dissolved in water. Soda is not a good beverage for children. It's very acidic. I don't recommend that you drink too much soda. It has a lot of sugar in it. And it's very, very bad for your teeth. Keep in mind that the acidity in soda will eat away at the amalgam on your teeth. And if you're a big Coke drinker, that is a colored beverage, and it will stain your teeth, and your dentist will probably love you. But I don't recommend it. I know growing up, my sister used to drink a lot of Diet Coke, and when she went to Europe, I think she was like, I don't know how old she was, maybe 22 after college, and they didn't have Diet Coke over there at the time, so she drank Coke because she couldn't give up her soda. And she came home with about 9 cavities. I thought my mom was going to kill her. So I had already had my cavities already because Mommy gave me too much soda growing up. It's all her fault. You can dissolve water in vinegar. So any liquid in a liquid, we already mentioned the 70% isopropanol, etc. And then the most common solution is this one, dissolving solids and liquids, such as salt dissolving in water. And you will be making solutions 2 different ways. I've designed a mini lab for you because I think it really teaches you how to make solutions. You'll first dissolve a solid in a liquid, and then you'll take that liquid solution and dilute it further to make another solution. It's a fun little lab. The kids really like it. At first, sometimes you're a little bit confused because I don't give you all the instructions for the second solution you make because you have to think it through. But you'll figure it out and do very well with it. If your solvent's a solid, your solution will be a solid. You can dissolve a gas, liquid, or solid in a solid. Gas stove lighter is hydrogen gas dissolved in solid palladium. The old-fashioned fillings, and I think I still have one silver filling, is mercury dissolved in silver. They don't really like to use those anymore. Mercury has been shown to be a carcinogen, so you don't really want mercury in your mouth, even if it is at very low concentration. Many of you have gold and silver plated jewelry, and you'll find your alloys there as well. You can have silver dissolved in gold. Gold is more expensive than silver, so it does depreciate the value, but it's a way to have pretty jewelry without it costing a fortune. As I said, whatever the solvent is determines what the solution is. So if you dissolve salt in liquid water, your solution will be a liquid, or we say aqueous because the solvent is a liquid. Couple definitions you're going to see here, and again, some basic review. Solvation is the process by which a solute dissolves in a solvent, and we can see that process right here.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloral.
Is that compound covalent or ionic? Ionic, you've got ions, and you've got a metal, non-metal, metallic cation, non-metallic anion.
5 ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
And one thing I do want to make clear to you, because we didn't harp on this in any regard earlier in the year, there is a difference between decomposition and dissociation. For example, with decomposition, you can have a reactant such as hydrogen peroxide decomposing to water and oxygen gas. And at your level this year, I only wanted you to recognize you have one reactant and more than one product. But these products are simpler substances, elements and or compounds. With dissociation, again, you will have one compound such as sodium chloride, and when dissolved in water, the ions will dissociate. So you generate ions in dissociation. And you can have a binary compound such as sodium chloride, or you could have, for example, potassium sulfite, where you have 2 potassium ions and 1 sulfite ion. So that's dissociation as opposed to decomposition, and we'll be talking more about dissociation as we go through. So salvation is the process by which the sodium chloride, a solid, would dissociate into ions, and you would see the water molecules hydrating or forming hydration shells around the ions. Generally speaking, salvation is determined by how compatible the solute and solvent are, and as a general rule, likes dissolve likes. So if the solute and solvent are both polar covalent, then one will dissolve in the other. If the solute and solvent are both nonpolar covalent, then one will dissolve in the other. If they're not similar, typically they don't dissolve one another. And I do want to take a minute to go back and review this concept. If you have a covalent compound, keep in mind that covalent compounds have covalent bonds. And is a covalent bond formed through the sharing or transfer of electrons? Sharing of electrons. And keep in mind that those electrons can either be shared equally or unequally. In a polar covalent bond, the electrons in the bond, so let's say the bonding electrons are shared unequally. And in a nonpolar covalent bond, the bonding electrons are shared equally. One thing I will remind you of is that a C to H bond is nonpolar covalent. And that's what you're going to see in your alkanes such as hexane, ethane, in a lot of your oils. Polar covalent bonds, O to H. For example, a polar covalent molecule would be water. For example, hexane, which is C6H14, is a nonpolar covalent molecule. So these two substances are unlikely to dissolve in one another because they're not likes. And that has a lot to do with intermolecular forces. We're not going to go into the intermolecular force reasoning behind this. At your level this year, we'll just go with the likes dissolve likes. For those of you interested in pursuing it further, we can talk about why that is. All right, so let's take a look at the following table. Again, if the solute and solvent are both polar covalent, the solution is likely to form. Sugar is a polar covalent molecule, and sugar will dissolve in water. Salt is an ionic compound, and most ionic compounds do dissolve in water. Some don't, and we'll talk about the ones that don't in a little bit. If you have a nonpolar solute such as oil, it's not likely to dissolve in water. And you know, if you make anything very oily and you try and just wipe it off with water, it's not coming off because their polarities are different. You would soak it in soapy water because then you'll get a more nonpolar nature in there due to the soap to try and get the oil off. A polar solute such as sugar and a nonpolar solvent such as hexane are unlikely to disperse evenly through one another, so the sugar is not likely to dissolve in the hexane, nor is an ionic compound such as salt. Nonpolar solutes are likely to dissolve in nonpolar solvents. So wax, which is nonpolar, is likely to dissolve in nonpolar hexane. How many of you have ever made candles? So what was your solvent with the wax? Do you recall? Do you have your kit at home? And it's going to be some type of organic solvent, so one dissolves in the other. So again, you either want both the solute and solvent to be polar or both to be nonpolar in order for one substance to dissolve in another. When one substance dissolves in another, we say it is soluble. If the substance does not dissolve in the other, we say that it is insoluble. What'd you get on the candle?
Ethanol or acetone.
Really?
Really? Non-polar organic solvents.
Yeah, but ethanol is polar and acetone is polar as well.
That's what this says.
Well, it does have, the acetone has some hydro-
Toluene or xylene?
toluene.
Yeah. That's what it says.
What about benzene? But see, benzene has been shown to have organic, to have carcinogenic nature. So benzene is in fact nonpolar.
It blocks chemistry.com. Schoolissue.chemistry.com.
Toluene, is that, I gotta think, but I'm thinking toluene looks like this. Do you have it on your screen? Is that toluene? I don't remember. Look it up, look it up. Toluene.
Oh, I found it.
Ooh, I drew it right. I had to think back 30 years and I remembered.
Think back to what?
Think back to high school. Yeah, that's it. So this is toluene right here. And toluene is a nonpolar covalent substance. So yes, something like wax would be soluble in toluene. So that would be a good solvent for it, provided that it's not harmful. Kids under 18 are not allowed to play with organics. It's dangerous. All right. Anyway, there are exceptions to these rules. Sugar is polar, and it's water soluble, but it's not soluble in ethanol, which is also polar. DDT, which is an insecticide, is nonpolar, so you wouldn't think it would be a problem if it gets in the water supply. However, at very low concentrations, it is water soluble, so they have banned certain insecticides such as DDT. How many of you know anything about the Vietnam War? Do you? What was the substance that they sprayed from the planes to kill the foliage?
No.
That was the frog one.
That's fertilizer.
It's agent something.
Agent.
No.
What?
It's a color. You've never heard of it?
Agent blue.
No.
Agent yellow.
Agent Orange. And you can ask Miss Mataskill more about the Vietnam War. But
We didn't learn about the Vietnam.
nothing?
Here it is.
We learned about international.
Agent Orange.
Do you I don't know how far. I don't think you go that far in APUS. Yeah, you go to the present in APUS next year, right? I don't know. Anyway, with the Vietnam War, a lot of that war was fought in forests, and they couldn't find the enemy, to keep it very simple. So they were spraying a lot of the areas to kill all the foliage off so that they could find the enemy. And one of the things they were using was Agent Orange. And they thought it would be perfectly fine because it didn't appear to be water soluble. Yet at very low concentrations, it does have some solubility. And what they were discovering is when the veterans, when they came back home, they were developing very rare forms of cancer, as well as having children who had malformations, and they were able to show that a lot of it, without getting into any of the chemistry, had to do with Agent Orange, and so that is a banned substance as well. But in regard to the chemistry, you can't just consider likes dissolve likes. You also have to consider different concentrations of the substance when you're looking for solubility in water. So there's more to the story than likes dissolve likes. But if we're looking at whether substances dissolve in water, we are going to follow some general solubility rules. And these rules are here. You do not need to memorize the solubility rules because they will be given to you. You have to be able to apply them. I'll go through the rules with you, and then I'll show you how to apply them to a series of examples, and then you'll have some examples that you can work through to make sure that you're understanding. First rule is that all common salts of the group 1 elements and ammonium ion are soluble. So if you look at these compounds here, any compound that starts with a group 1 ion, such as lithium ion or cesium ion, or ammonium ion, will always be water soluble regardless of what it's connecting to, regardless of the anion. If the cation is from group 1 or ammonium, you have a water soluble substance. All common acetates and nitrates are soluble in water. So any compound that contains an acetate ion, that'll be the back end, the anion, or a nitrate ion is soluble in water, except silver acetate is not water soluble. Insoluble, in means not. So calcium acetate and aluminum nitrate are water soluble. If you see acetate or nitrate, provided that the acetate is not connected to a silver ion, it's water soluble. This one's a little tricky. It says all binary compounds of group 17 elements. So all binary compounds of group 17 elements. What does binary mean? 2. 2 capital letters, not 3. And it's got to contain a group 17, other than if it contains fluoride ion. With metals are water soluble except those of silver, mercury 1, and lead. So calcium iodide is binary. It doesn't contain one of those cations, and it doesn't contain fluoride. It's water soluble. Magnesium bromide, water soluble. Nickel 3 chloride, water soluble. Be careful with mercury 1. This is one of the knots. It's a little bit tricky. Mercury 2, you would guess correctly. Mercury 1 is a polyatomic on the back of your periodic table. This is mercury 1 ion. So that one's a little bit funky. I try and stay away from it for you. Rule 4 says all sulfates are soluble except those of calcium, barium, strontium, lead, silver, and mercury 1. So most sulfate-containing compounds are soluble, but not calcium sulfate, not barium sulfate, not strontium sulfate, not lead 2 sulfate, not silver sulfate, not mercury 1 sulfate. So magnesium sulfate, aluminum sulfate, copper 2 sulfate are all soluble. And then rule 5 is sort of a catch-all. It says except for those in rule 1, that is group 1 or ammonium containing ions, carbonates are not water soluble. Hydroxides typically not, but calcium, barium, and strontium hydroxide from group 2 are. Oxides are not. Sulfides are not, but group 1, group 2, and ammonium ion are. Phosphates are not. If there's no rule for it, assume that it's insoluble. It doesn't dissolve in water. Let's take a, oopsie, I should get those answers out. Let's take a look at the following table. We want to figure out if the substance listed on the left is soluble in water, You want to indicate if it is or it isn't with a Y or an N for yes or no respectively. And then I like you to indicate the rule so it's not a 50% chance of guessing correctly, but also if you can find the rule, you understand it better. In the first one, it says sodium chromate. Sodium, for sodium ion from group 1, all group 1 containing compounds are water soluble. So this would be yes, rule 1, as stated here. The second one says nickel 2 fluoride. What do you think?
No.
Why?
Contains fluoride ion.
Rule 3 is correct. It contains fluoride ion and it's not hooking with group 1 or ammonium ion. Calcium sulfate. There's a rule for sulfates. Look at that rule. Is that a yes or a no? That is a no. Rule 4. Magnesium hydroxide.
No.
That is a no. Rule 5. Good. Aluminum sulfide. What do you know about the sulfides? Most of them are not, except group 1 and group 2. Aluminum is in group 13. Strontium acetate would be yes, and that is because of rule 2 is correct. Good. Copper 1 nitrate. All nitrates are water soluble. Magnesium sulfide. Most sulfides are not, except group 1 ammonium and group 2. So this is a
Yes.
yes. Lithium hydroxide. Most hydroxides are not, except group 1 ammonium containing, as well as calcium, barium, and strontium. So this is a yes. This can be rule 1 or 5. You can pick whatever one you want. Don't list 2 rules unless you're sure of it. 1 rule is sufficient. Ammonium fluoride. That's a yes because any ammonium containing compound is water soluble. All right? And you'll get more practice with this concept in your classwork. 2 more things we want to mention. When we talk about solubility, very often we talk about solids dissolved in liquids. When you're talking about liquids dissolved in liquids, you tend to use the word miscible if one liquid does dissolve in the other. If it doesn't, we say immiscible. The prefix im means not, like something that's immeasurable, can't be measured. Someone that's immature is not mature. All right, last thing I want to talk about is something you probably have heard a little bit about in environmental management. When you talk about contamination or pollution in the air, for example, have you seen the unit parts per million or parts per? Yes. So that is a unit of concentration. There are many ways that concentration can be expressed. The most common way is molarity, and in many of the solutions that you've used in the lab, you've seen molarity already because it'll say on the bottle that you're using 1 capital M for molar. So concentration is the ratio between the amount of solute and either the amount of solvent or solution in which the solute is dissolved. There are many, many ways to express concentration. One of the key ways is as molarity. Molarity is abbreviated with a capital M, and that is moles of solute per total volume of solution in liters. You can solve for moles, you can solve for volume, you can even find mass by going through the moles, you can solve for molarity. So we're going to walk through 3 very easy examples, and then you will have time to work on this concept. It's very simple. It's critically important. The first example says calculate the molarity of a solution. It could say calculate the concentration of solution as well. So that is what we are looking for. It's made by dissolving 2.50 moles of sodium chloride. That's my first given, in a final volume of 500 mils of solution. So let's get the information down, and you'll see that this is really very, very simple. So in this first problem, we want to calculate the molarity, and very often they'll just ask you to calculate the concentration of something. If they don't specify the unit, they probably mean molarity. So concentration of sodium chloride. These brackets here indicate concentration. We're told that we have 2.50 moles of sodium chloride, and our final volume is 500 mils of solution. Now, concentration in this case as molarity is equal to moles of solute over the total volume, T for total volume of solution in liters. So the concentration of sodium chloride, in this case molarity, is 2.50 moles over, I need this in liters and this is in mils. I'm going to move the decimal 3 to the left, which some of you were confused on your quiz. We need to fix that. And that is equal to 5 molar. That's our concentration of the sodium chloride. And that's as easy as it gets. Number 2 is a little trickier, but not something that you will find overly challenging. In number 2, it says calculate the molarity of the solution. So again, we want to know the molarity. That is to say, we want to know the concentration of lithium sulfide. The mass of it is 24.8 grams. And the final volume of solution, that is the total volume, is 750 mils. Well, molarity is moles of solute over the total volume of solution in liters. So what are we going to do? We're going to convert to liters for sure. And what else must we do? Convert the mass to moles. So 1 mole of anything is equal to its mass in grams from the periodic table. And that's 24.8 divided by 45.948. And that's 0.540 moles of lithium sulfide. How do I get the molarity? I'm going to divide this by the volume in liters. and that's 0.720. You can write moles per liter, or you can write capital M as the unit to the right of the number to make a quantity. And the last problem says calculate the mass of sodium perchlorate that's dissolved in 100 mils of solution to generate a 0.500 molar solution. I abbreviate solution SOLN very often. So in number 3, we want to get the mass of sodium perchlorate. And again, if you are having issues formula writing, you just killed the problem. Be careful. The volume is 100 mils, and we know right away we need that in liters by moving the decimal 3 to the left. The concentration of the sodium perchlorate is 0.500 molar. Well, this problem's a little different. How will we approach this? We want to get mass. What do we have to get first? Moles. So we know that the molarity, abbreviated capital M, is moles of solute over the total volume of solution in liters. So first I'm going to go after the moles of solute. That's equal to the molarity times the volume total in liters. So that's 0.500 molar times 0.100 liters, and that's going to be 0.0500 moles of sodium perchlorate. How would you get to mass? Using the periodic table. So in this part, I solve for moles by multiplying molarity times the total volume of solution in liters. I get moles, and then 1 mole of anything, and this we learned back in chapter 7, and you'll see these concepts coming back again and again and again and again. That's a little sloppy up there, but I think you can make it out. And that's a mass of 6.12 grams of sodium perchlorate. The molarity calculations are very, very easy. You want to know that molarity is moles of solute per total volume of solution in liters. So there are many ways to express concentration. Molarity is just one of them. We'll explore some of the others later in the week. Your take-homes are that there are 9 types of solutions. You want to understand the solubility rules and be able to apply them effectively, and you'll get a lot of practice with this next time.